Now that we know about matrix products and their properties, let us revisit the topic from the previous course, row reduction. To solve a system, for example, you learned about 3 elementary row operations you can perform on a matrix. Interchanging 2 rows, multiplying one row by a non-zero scalar, and adding a multiple of one row to another row. All of these elementary row operations can also be described in the language of matrix multiplication using so-called elementary matrices. This is promising since it will allow us to apply our knowledge of matrix multiplication in the setting of row reduction. Let us walk through the operations one by one. The first elementary row operation interchanges 2 rows of the matrix. This turns A into B. To capture this concept in the form of matrix multiplication, we take a 3 by 3 identity matrix. Note, 3 is the number of rows of our original matrix. We perform a row operation on this identity matrix. The new matrix is called an elementary matrix. To analyze what happens once we multiply A from the left by this elementary matrix, we take a row by row perspective. The first row of EA is a linear combination of the rows of A, using the elements of the first row of E as coefficients. 0 times row 1 of A, 1 times row 2 of A, plus 0 times row 3 of A. This is exactly the second row of A. Next, we construct the second row of EA, using the second row of E and the whole matrix A. We get 1 times the first row of A, plus 0 times the other rows, which is just the first row of A again. Computing the third row of the product, we obtain some zeros plus 1 times the third row of A. Take a look, it does the trick. Multiplying by this elementary matrix interchanges the first and second row of A. So the matrix B we obtained by our row operation is equal to the product of E and A. Next up, multiplication of a row by a non-zero constant k. For our example, we use row 2. Matrix A on the slide is row equivalent to B. Since our example matrix has 2 rows, we construct our elementary matrix using a 2 by 2 identity matrix. Perform the row operation, and voila! Here is our elementary matrix. Once again, we compute EA. Using a row by row perspective on matrix multiplication, we see that multiplication by E leaves the first row of A as it is, and multiplies the second row by K. Once again, we see that EA equals B. The elementary matrix describes our row operation in matrix form. The final elementary row operation adds a multiple of one row to another row. This turns our new example matrix A into B. Our example matrix has 2 rows, so we build our elementary matrix using a 2 by 2 identity matrix. We add the second row k times to the first row to obtain E. Compute the matrix product EA, row by row again. The first row of EA equals 1 times row 1 of A plus k times row 2 of A. The second row of EA is just row 2 of A. So once again, EA is exactly the result of our row operation. We haven't proved a thing, but looking at these examples, we do see a pattern in how to capture elementary row operation in matrix form. To create an elementary matrix that captures a certain row operation on an m by n matrix A, perform your row operation on an m by m identity matrix. The result is called an elementary matrix, E. The product EA is then equal to performing the row operation on A. That is, EA equals B. This use of elementary matrices allows us to describe row operations in the language of matrix multiplication. This gives us a new perspective and allows us to apply our entire toolbox of computation rules for matrix multiplication in this setting. That will definitely come in handy in the next couple of videos. See you there!